Thank you, everybody, for being here, coming back. My name is Marco Esters. I'm a postdoctoral associate here at Duke University with the Cortorola Group. And yesterday, we learned about how to look at our database, query our database, and retrieve data from the database. And today, I will talk about structure analysis and structure generation, so you can generate your own input files for your own DFT calculations or your own your machine learning models. This work is primarily based on the work that Dr. David Hicks did during his PhD with us and during his postdoc here. All of these modules, AFLOW-SYM, the Prototype Encyclopedia, and AFLOW-XtalFinder were his work. So, and thanks, David, for providing a lot of material to me as well here. Looking at structural analysis and automatic structure generation is primarily inspired by the desire of a material scientist or a chemist or a physicist to figure out the relationship between structure and properties. Two important aspects are there are two important aspects to that search. One is, how does the symmetry affect the structure? And there's one very well-known phenomenon where that is immediately apparent, and that is piezoelectricity. If you have a structure with an inversion center, for example, a half-Heusler alloy, as we can see here on the left, and you apply pressure on it, you will generate an electric field and thus a voltage. Perovskites are also another important class of material where that is the case. If you look at, for example, diamond at the bottom, you do not see that, and you have an inversion symmetry, and when you apply pressure there, you do not generate that electricity. So lack of inversion symmetry creates a voltage. Inversion symmetry does not create a voltage. Another and probably more intuitive case where structure property relationships are important is the atomic decoration. When we look on the right, there's a half-Heusler alloy, and if we place different types of atoms on the crystal sites, we get different properties. That's a very important part of materials generation and materials exploration. The example that we see here is the half-Heusler alloy with platinum and antimony and a third metal. In the top, we see scandium, then terbium, and then holmium. And we see that the band gap changes depending on what the third element is. So these are the two aspects of structure and properties that we are trying to explore. We will start with the first aspect. At the beginning, I will talk about symmetry, what the pitfalls are, and how we determine them, and how you can use our features, especially our online features, to get symmetry information that we need. The other one, the second part, we'll talk about how we can generate these decorated prototypes. And the last part, we talk about similarity matrix and how we can generalize the prototype principle. Why care about symmetry? I already gave you an example about why symmetry is important, but symmetry is really just more than piezoelectricity. Symmetry is everywhere. The most prominent example that you probably have all seen if you've done anything with materials are band structures. The entire x-axis of a band structure diagram are points in the Brillouin zone. The labeled points are high symmetry points. Here we see on the left, we have the gamma point is always in the center, but we have these L, K, W, U, and X points. And this X here is the same point as the center here on that one. And we know that because of symmetry. And with symmetry, we can reduce the Brillouin zone into the irreducible part, which is the only part we actually need to calculate. The rest can be determined by symmetry. Another thing where you've seen symmetry, if you've done any kind of crystallography, you see descriptions like material X crystallizes in space group, for example, 225. Somebody who knows a little bit of crystallography knows immediately how this compound looks like based on the space group, or at least has a good idea about how the structure might look like. And there's a lot of other symmetry classifications that we can do, and these are very important. They are all based on determining symmetry elements. Another thing that symmetry can do is make our calculations more efficient and less burdensome. For phonons, for example, where you have to distort an atom into into three independent directions, you can reduce the computational the number of calculations, computational effort using symmetry. If, for example, distorting an atom into X is the same as distorting it into atom Y, except for that you have a rotation, why do the second calculation? And phonon calculations are expensive. Your DFT code, the DFT code that you're using is actually already doing this, unless you tell it not to, by only looking at the K points that it needs to calculate based on symmetry. It's already reducing the number of K points for your calculations. And the last thing is we at AFLOW use symmetry to characterize our compounds. We've seen probably yesterday different space groups, different Pearson symbols. These are all symmetry classifications that we use, and they can give us a lot of insight about the structure of a compound. So what do we need for a symmetry package? There's two main requirements. The first one is it needs to be accurate. That's kind of a no-brainer, but it's actually very hard to do. A symmetry package that is not accurate is not a useful symmetry package. And the second thing that we need is we need it to be autonomous. We need it to be globally valid. If you have to keep fine-tuning parameters to get the correct symmetry, the symmetry package is not going to be very predictive. If you have to constantly monitor that it's doing the right thing, it's not a very reliable package, and it's also not suitable for high throughput, where you can't manually check every single symmetry determination. AFLOW-SYM successfully identifies symmetry for all 3.5 million entries in the AFLOW database without any human intervention. So how do we do it? How do we do this? We test for invariance of crystal under certain transformations. That is what symmetry operation of a crystal is. For example, mirror planes or rotations. And from that, we determine space groups, Pearson symbols, Bravais lattices, all kind of descriptors, the Wyckoff positions. We can determine the conventional cell, which is very common for crystallographers and chemists, because it's a very nice Morse orthogonal cell and easy to visualize. And we can also determine primitive cells, which is very important for computations because they're the smallest cell out there with the fewest number of atoms. How do we exactly identify what is a valid symmetry operation? The short answer is we do it and see if we have a match. So here we have a fourfold rotation. We apply the transformation and check, does the new structure map to the old structure? And there are three cases. The top one is easy. The atoms exactly lie on top of each other. It's a match. We're good to go. The second one, or the third one actually, the third one is also very easy. When we just do the animation again, you see that the two atoms with a fourfold rotation get mapped onto empty space. This is not a match. The symmetry operation is not part of the crystal. So that is also easy. But what about the second one? The second is actually the most common, where you don't have an ideal match. It can have a lot of reasons. One being, an imperfect input structure. The other one could be numerical noise. You will never get to an exact zero difference when you're mapping. If you have a difference of 10 to the negative 14 angstroms, that's close enough. But what is close enough? At what point do you cut off and say this is a match? And we call this epsilon here, or a threshold for mappings. And this is essentially a radius. In this case, your circle in the 2D view, or in 3D is this is a sphere around the atom. And if the point lies inside that sphere or inside that circle, we consider this a match. And we do this with all atoms inside the material. And if everything is below the threshold epsilon, or at the threshold epsilon, we consider this a good symmetry operation. There are a few caveats to this. One being the periodic boundary conditions. We have an infinite crystal. It's not like with molecules that we can just map the atoms. We also need to take care of that this extends properly to all three dimensions infinitely. And we may have mappings in non-uniform metric space. What this means is something I'll explain in a minute, but these are the conditions and the restraints that we are looking for and that we need to take care of. AFLOW-SYM does a lot of mitigation of these problems, the threshold and the non-uniform metric spaces. It does three things, essentially. It maps both in direct and in reciprocal space, and that is extremely important. If you just map in one of the spaces, and or if you have your direct space and your reciprocal space will give you different symmetries or does have inconsistent symmetries, you do not have a proper symmetry description. It needs to map everywhere, and we do both of them. And a lot of codes are actually struggling with this, especially codes that are only looking at the direct space may get wrong matches or inconsistent symmetries. The other thing we need to be careful of is the so-called non-metric sample space. We can imagine in Cartesian space, when we have our epsilon sphere, for example, a cutoff of 0.1 angstroms, this is going to be a sphere of the radius of 0.1 angstroms. If we're in cubic, that's all okay. But if we go to fractional coordinates in a non-cubic compound, things are starting to change. Fractional coordinates only go from 0 to 1 in all 3 dimensions. So if you have a 0.1 angstrom sphere, it's going to warp. If we take for example, the tetragonal cell, which has a different c-axis, for example, a longer one, 0.1 angstrom along the c direction is going to look very different. It's going to be shorter than in the a and b direction. It gets even worse for anything that doesn't even have any right angles. The bottom example here shows what happens to a triclinic structure or monoclinic structure. This tolerance sphere gets completely warped in fractional coordinates, and that has consequences for how we determine things like the distance between 2 atoms, which we use as the metric, and it needs to be below the threshold. Here at the bottom we see a mirror plane where the distance in Cartesian coordinates is this one here to the next cell, but if we do this in fractional coordinates and have the square, the minimum distance in fractional coordinates can become this one here. And that has consequences for how we determine our threshold epsilon. The other problem, the other caveat is the threshold epsilon itself. What is a proper epsilon? What is a proper threshold? The answer is that depends. When we look at the part in the middle here, you see that the answer for this particular system, which is part of the ICSD database, is an experimental structure. The symmetry depends on what you consider to be a proper threshold. It can range from monoclinic to orthorhombic to rhombohedral to FCC. And we even have a certain part here in the middle that has no color assigned to it. And this void region is where symmetries between direct and reciprocal space are inconsistent. So AFLOW-SYM, when it encounters a tolerance like this, shows that the symmetry is inconsistent, then it does a tolerance scan. It increases to a lower and a higher tolerance until it finds a consistent symmetry. And the last mitigation effort that we do is we define a system-specific tolerance. Instead of saying the tolerance is 0.1 angstrom, we say that we depend our tolerance on the system. 0.1 angstrom might be good for a lot of systems, but for other systems, it might be a terrible idea. You can imagine that a system with a very large volume, 0.1 angstrom is not that much. If you go to a small volume, 0.1 angstrom percentage-wise is just a lot larger and will have a lot bigger impact on whether or not we consider a symmetry operation a match. So what AFLOW-SYM is doing is it just defines 2 tolerance criteria. A loose tolerance criterion, which is 10% of the minimum nearest neighbor distance. So it determines all the distances and takes 10% of it, and that is going to be our epsilon. Another criterion, which is the default in AFLOW, is the tight tolerance criterion, which is 1% of the minimum nearest neighbor distance. That has the advantage of that we have a single global tolerance. We don't have to do any kind of fine-tuning of which tolerance we use for which system. Some require an angle tolerance, and some even require different tolerances for different rotations or different symmetry operations. With AFLOW-SYM, this is not the case, and it is not needed. So I can tell you all day long about why this is better, but it's better to see the evidence. So how can we benchmark this? We did benchmark it by comparing with experimental structures and compared this with other codes that are out there. And we can see that AFLOW plain and simply outperforms the codes that are currently available. the very popular codes are FindSim, Platon, SPGlib, and we did a comparison in 2018 when the paper came out, and just showed how accurate are these codes, are these packages, and how accurate is AFLOW when we compare it to experimentally reported structures. And we see that AFLOW has the fewest number of mismatches. A mismatch is when the determined space group is different from the reported space group. And we see that there's especially a huge mismatch with the hexagonal structures. Here for FindSim and SPGlib, we can't even fit that here on this graph. You see here the inset. So what we tried afterwards, or what was tried afterwards, is we tried to optimize the tolerance or find a different tolerance in it for the other packages, and it did improve somewhat, but it still does not go anywhere close to what AFLOW can do. So all these mitigation factors, the universal tolerance, the tolerance scan, the consistent symmetry checks were vital in making this symmetry package more accurate compared to experimental structures. And in the end, the experimentalists are the ones that we need to focus on and we need to benchmark against. Are there any questions about the background and what I just talked about? Go back.
I have a simple question.
Yes.
Marco, how come for hexagonal structures, that's where there's a lot of problems?
That is a very good question. I'm not sure if we have figured this out, but we assume that the threefold and the sixfold rotation, especially the sixfold rotation, is very, very difficult and error prone. Another thing that I think we need to keep in mind is this non-metric space, because we have for hexagonal, we have a 120-degree angle, and essentially there's probably going to be a lot of error when we put this into fractional coordinates and make that that comparison.
Okay.
But yes, it's staggering just how many issues there are with the hexagonal structure.
Okay.
And Marco, I just want to add that you'll see that other codes, this is an issue across the codes. It's not just AFLOW. So hexagonal is a problematic symmetry to identify. Yeah, these smaller angles, or of course, either the corollaries, you have the bigger angles too, but this is going to cause a lot of warping in that space.
Rhombohedral, when we're looking at rhombohedral, which can also be displayed in a hexagonal way, they're also very difficult, because of this. Sorry, go ahead. I think I was interrupting you.
No, it's okay. I just want to add that that to what Marco was saying, that it's very important that we have this consistent way of identifying the symmetry, also because we don't necessarily know what the error is in the experiment. And so you can imagine that every structure comes with a particular error, which is different across each system, that needs to be identified and dealt with individually. And so this way of doing it in a commensurate way, where you validate against the properties of the space group, is really the only way to do it.
Yes,
experimental data. Go ahead.
That's correct. We don't necessarily know what the quality of the experiment is, whether or not the structure was determined with single crystals or neutron diffraction, using Rietveld refinement, or just with HKL indexing. Yes, the quality of the experimental data might cause a problem. So the more self-consistent we are, the better. Thanks for bringing that up, Corey. It was important.
Okay, thank you.
Okay, any more questions? How did we decide 1% and 10% for the tolerances? Because they worked, I think is the answer. They are also, because they gave very accurate, good results and were reasonable tolerances.
Yeah, so we have the I can talk a little bit about this. We did a benchmarking for the database that we have, the large set of structures, and so we played with these tolerances. It's largely a heuristic, but using these tolerances, this loose and tight values, between the two, we can really nail the symmetry that we expect for the structures across the board. And so this is also what comes with the power of a big database, you have a lot of different checks that you can do, you know, and you know that if something works for 50, 60,000 structures, that you have results to compare against, you know that you have the right values.
Very good questions. Any other questions? Doesn't appear to be the case. I will move on. So what kind of symmetry operations are we actually looking at? Basically the ones that with the minimum amount that we need to describe a crystal. Anybody here more familiar with molecular symmetry will know the rotations and the inversions and the roto-inversions. We also look at the specific ones for a crystal, which are glide planes. So these are translations with an accompanied mirror plane and screw axes. These are the main symmetry operations that we are looking at. We can determine a various number of crystallographic symmetry groups or relevant symmetry groups, the point group of the lattice and the point group of the reciprocal lattice. Then the factor group, that is a very important one, which includes not just the rotations and the roto-inversions and all that of the crystal, but also also contains the translations inside the cell. We can get the crystallographic point group, which is the actual point group of the crystal faces. We can get the dual of that by for the reciprocal cell, and that is the Brillouin-Zon symmetry, which is what these the Brillouin-Zon paths are based on. The Patterson symmetry group, the space group of the material, and the site point group, which is the point group of each and every atom. The last one is very important, for example, for force constant transformations. So we calculate a lot of different symmetry groups that are used for different things. Another thing we determine is the crystal spin symmetry. You can, here as an example, the crystal on the left has a space group number 229. It's body centered. But if we start adding spins to the atoms, we are breaking the symmetry. This degree of freedom can break the symmetry. It doesn't always, but it can. In the example on the right, where every alternating layer has a different spin, we lose the body centeredness and we get a space group of PM3 bar M, or space group 221. The crystal spin symmetry is never higher than the crystal symmetry. It's always lower or the same. Just to clarify, it's not the same as the magnetic space group. This is just the symmetry, basically treating atoms with different spins as different atoms. Another thing we provide are symmetry descriptions. We provide basically all the common ones that are out there, the space group number. We give the space group in the Hermann-Mongan notation, the Schoenflies notation, Hall symbol, and Pearson symbol. We also are consistent with the International Table for Crystallography, providing Wyckoff multiplicity, Wyckoff positions, and the representative coordinate. The Wyckoff letters can be used along with the tables and the coordinates to expand the coordinates. Here, in the case of silver, when we put this at the origin and we know what the space group is and what the Wyckoff letter is, we know that this can be expanded to 0, half, 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 0, half, 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 0. So it basically occupies the origin and the faces, the center of the faces. So it's an FCC compound or some other face-centered space group. That was a lot about how we do it and what we do. So let's talk about how we can actually use it. And for that, we go to AFLOW Online in just a little bit. We have two things, but I want to highlight that we can also visualize symmetries. You saw entry pages yesterday because of, Dr. Rose has shown some entry pages, and we have a structured visualization tool there that we can use to visualize symmetry operations. And that is exactly what we're going to do right now. I'm going to move over to my browser and remove all the Zoom stuff out of the way and go to aflow.org. So let me increase the font size maybe a little bit. Is that visible? Somebody give me a thumbs up if that's good.
Yeah, this is fine. Thanks.
Okay, thank you. So we go to the Mendelib search, and we will look for something easy: sodium chloride. Number of species being 2. And once it gives me something, we will just take the first entry. I will put that link in the chat as well, if you, so you can just go follow along. So here we have the crystal structure visualization. It's sodium chloride, it's rock salt. And if we can look at this from all different perspectives, if we go to the symmetry tab here, we see that we have 48 symmetry operations, and here they're all listed. There are descriptions. Here are the notations for the Hamann-Morgan and the Schoenflies notation. And let's take, you can also visualize the symmetry axes. Let's take, for example, this one here. This one here is just a twofold rotation. And when we click apply, you see that we rotate it, and if we rotate it a second time, it goes all the way back to the unit cell. We can also show just the supercell for visualization. Let's take something more exciting than a twofold rotation, and we can have a mirror plane. This here, or this plane here, and if we click apply, see it's being mirrored. If we click apply again, we get back to the origin. Something very special are roto inversions. We have because they have an axis and a point, and we can click on this, and it does the rotation first, and then the inversion. And since this is an S4, for applications of this roto inversion should go back to the origin, which is exactly what we see. Any questions about this visualization? Doesn't appear to be the case. Feel free to play around with it. It's a very neat tool. You can essentially visualize every single symmetry operation that we have here. The S3, for example, goes through the diagonals. So yeah, try it out, and if you're unsure about a symmetry visualization. Another thing I want to highlight is our symmetry package, which was on the last slide on the left. And for that, we go to AFLOW Online. AFLOW Online is when you go to the home page and you go click on this one, or you can follow the link that I'm putting in the chat. AFLOW Online is our interface, or online interface to AFLOW. There are certain features that you can use online without having to install the entire AFLOW package. We will not be going through all of the features of AFLOW Online, just the symmetry stuff, but it is you feel free to play around with this one a little bit more. We will focus on the symmetry. This is our input structure. It's written in the VASP format, but AFLOW Online understands any kind of structure format that we are aware of. Quantum Espresso, it understands Quantum Espresso. It understands CIF, AppInit, ELK, understands ELK, and different VASP formats. And this one here is an iron potassium oxide. And you can manipulate the structure files. You can, for example, convert this one to Quantum Espresso by clicking on the structure format conversion, click on Quantum Espresso, and then you click Submit. And what it does is it returns your structure file back in Quantum Espresso format. Bottom here is a back to top button, and that is what we're going to click on and to check out the symmetry stuff. Let's determine the space group, and there we already see we have a certain choice of the setting, and that is because some space groups have different settings according to the International Table for Crystallography. Let's see, we can just take the setting 1. There's unfortunately never a more intuitive way of expressing it. It's just setting 1 and setting 2, and let's compare the two. Here we get the space group number. It's 227, so it's a spinel-like structure, and the space group is FD 3 M. We get the Hall symbol, the Schoenflies symbol, the Lauer class, and the crystal class, and we see the origin of the structure. And if we scroll back to the top and maybe change the setting to 2, we will see that just commit this origin here to memory is 0, -1/4, 3/4, that the origin is different. This is just a different setting, it's a different origin choice. Not every space group has it. This one happens to have it, but not all of them do. Roxa, for example, doesn't have a different setting. It will work the same either way. Then what we can do is we can determine the Wyckoff positions. Wyckoff positions are the unique positions. And setting 1 for the Wyckoff position gives us 3 different Wyckoff positions, 1 for iron, 1 for potassium, 1 for oxygen. And the multiplicity already tells us kind of that in the conventional unit cell, we have 8 iron atoms, 8 potassium atoms, and 16 oxygen atoms. But only 3, each one of them has only 1 symmetry inequivalent atom. Since we have different origins for the different settings, we can just go and see what it looks like with setting 2. And you see when you compare the two, here is an 1/8, an 1/8, and an 1/8 for iron, and here it's 0, 0, 0. The Wyckoff positions themselves have changed, but not the symmetry and not the labels. So we have differences here in the origin primarily with the different settings, but they're all valid. They're all good Wyckoff positions, they're all good structures. Another thing that AFLOW can determine is the Pearson symbol. This is another symmetry descriptor. We click on that one and let it go. We have CF32, which means it is face-centered and the conventional unit cell has 32 atoms. We already got to that conclusion that the conventional cell has 32 atoms because when we're looking at the Wyckoff multiplicities. Here, 8 plus 8 is 16, plus 16 is 32. And this is what the Pearson symbol also symbolizes. Everybody following along? Any questions about this? I don't see any questions. So I'll introduce the other features. The AFLOW prototype I'll reserve till later. But another important thing, a crystal point group, you can determine what the crystal point group is. We see it is the Schoenflies notation OH, so it's an octahedral point group, or in Hermann-Morgan's M3'M. The point group order is 48, which means it has 48 symmetry operations, or 48 different rotation symmetry operations. Just keep that number in mind, and it belongs to the cubic crystal family. There's a question, Christian.
Yes, thank you, sir. I want to ask where is located the computer who is doing the simulation beyond, and is it a supercomputer?
No, is actually just a regular server. These calculations are not very difficult. It's just taking a structure, determining everything based on the structure. It does not do any kind of atomic simulations. There's essentially a public that is essentially addressing an API that runs AFLOW and returning the results. Why are there many different types of, does it answer your question?
Yes, thank you.
Hello, Marcus. Hello.
Hello, I can hear you, yes.
So you display the atomic position there the other time. Can you display the atomic position for a supercell?
This one here? This one here is the, these are the atomic positions in fractional
Hello?
coordinates. Can you hear me?
Yeah, fractional coordinates, you display
Yes.
that one. Can you do the same thing like if you have a supercell, can you do it for supercell?
If you can put in whatever file you want in here. If you put in a supercell, then yes, it will do that. If you're asking if we can generate a supercell, we don't have that feature in AFLOW Online yet,
Okay.
but I can write it down as a feature request. It's an easy thing to implement.
Okay.
So another question that I see in the chat here is, why are there many types of symmetry indicators for a crystal in the database? Why they're in the database is because there are a lot of different symmetry descriptors out there. Pearson symbols, space groups, all these different notations are all out there, and different crystallographers use them for different purposes. We want to display everything that could be useful for anybody. So we're showing a lot of different data. Whether or not you need it is a different question. That's why there's a lot of them in our database. And this is actually not a database. This is calculated on the fly. You can put any structure in there. We will calculate the information on the fly to you. This is not our database, even though the structure happens to be in the database. Okay. Any more questions? Oh, I guess
maybe just to follow up on that, Marco, that for most of the entries in the database, you will also see all this information.
Yes.
Yeah.
Yes. The data is, yeah, thanks, Cormac. Yeah, the data is available in the database, but this API here, this application does not use the database, but you can get the information. That's correct. Something I actually forgot to ask, everybody familiar with the VASP input format? What these mean? If anybody wants me to explain it, just raise your hand and I will go through it. Ah, there's a raised hand. Yeah, my apologies, I forgot to go over that one. So this first line here is just a comment line, and you can write whatever you want in there. This is just example postcard. This one is the scaling factor. These are the lattice vectors. So it's x, y, z of the first lattice vector, and this is of the second, and this is of the third. And the scaling factor is used to multiply, or all these lattice vectors will be multiplied with the scaling factor. The second one here is this one here, this line, I guess it's the fifth, if I can count, no, the sixth, is the species in the input file, iron, potassium, and oxygen. This line here is the composition. So there's 2 irons, 2 potassium, and 4 oxygen. This one here indicates that this is fractional coordinates. The alternative is Cartesian, and these are all the fractional positions. So the first iron is at 3/8, 7/8, 7/8, and this one, the second iron, is at 5/8, 1/8, 1/8. And then here we have the potassium coordinates, these 2, and the last 4 are oxygen. Just to show you how it looks like in Cartesian coordinates, calculate that as well. Here we see the big difference is Cartesian, and all these coordinates here are, some of them are 0, but a lot of them are listed as Cartesian coordinates in angstroms. That is the quick rundown. Any other questions about the stuff that I showed?
Sorry, Marco.
Mm-hmm.
This is the input for okay. Yeah, okay. I think this is input for FAB. This is for FABs. I can see the quantum expressor. I just want to know whether I can take other calculation code, other code.
Are you asking me if you can use a quantum espresso calculation?
Yes, quantum espresso.
You can input a quantum espresso file. Yeah, that's not a problem. It will, I mean, here's a quantum espresso, the structure in quantum espresso format, and you can do the very same calculations that you do. Can show you just to show you that I'm not lying to you. Here's the quantum espresso file format. And if we determine the space group here, you can see it is identical. So any kind of quantum espresso or app init format works with our interface. Then I see a question in the chat. Can we visualize crystal structure of polymer materials? The visualization on the entry page is just of the data we calculated. Other than that, if you have an input file, if you have a postcard or a quantum espresso file of that polymer, you can throw it in there. Yes, I think the limit of atoms that we have on our server right now is 50 atoms. If you have a unit cell that has more than 50 atoms, our server is going to say no to that one, because we don't want to overload our servers with very expensive calculations. Well, very good questions. Any more questions?
Thank you. Thank you.
All right. Then let's show some more features. All of them were these are fairly simple descriptors. Another interesting calculation, if you're ever curious about what actually your how these atoms relate to each other, you can click on equivalent atoms, and the output of equivalent atoms is oh, this is now in quantum espresso format. Yeah, it's now a quantum espresso format, but it'll be similar in VASP. We have 2 iron here, and you see the notation on the side. You have 0, 0, and then there's a multiplier 2. That means we have 2 irons, and they relate to atom 0. We're starting to count at 0. So this iron here is equivalent to this iron here. Same with potassium. They're equivalent. And with oxygen, all 4 are equivalent. They're all referring to atom number 4. Or in this case, since we start counting with 0, I don't know, 5. So 1, 2, 3, 4, 5. So we see the multiplicity, and we see which atom relates to what. So if you're ever curious to see which atoms map to which one, especially if you have a species in there that has 2 inequivalent atoms, you can use that functionality to check this out. Then there's, we can do some lattice information. We can look at the actual lattice. We see we have an FCC lattice. It's cubic, and we have the Pearson symbol CF32. Here are the alpha, beta, gamma values and the ABC values in angstrom, and we also have them in Bohr. I think app init users will find that very useful, that we have these values in Bohr as well. I'm not sure what Quantum Espresso uses, but I think app init uses Bohr. We can do the same with the reciprocal lattice. We can determine what the reciprocal lattice is, and we get similar output. And here are the lattice vectors, and we also get the reciprocal lattice designation. And if you know anything about reciprocal lattices, you will have already guessed that we get a BCC because our real space lattice is FCC. Here you see face center cubic, and the reciprocal lattice is body center cubic, which is good. We should get a BCC lattice with an FCC crystal in the real space. Then the supercell lattice essentially just gives you the lattice of your cell as if it was equally decorated. So we are ignoring species, and this is the lattice that we are getting. We will get the same thing. It's still going to be FCC, but I just wanted to show that this is an option. Then I already mentioned earlier that we can calculate different symmetry groups. All of them are here. I'm just going to show this as in the factor group. And this output is very large. You will see that there are 48 factor group operations. Let's look at one that is a little bit more exciting than the identity. Here we have a roto inversion. We get the rotation matrix in Cartesian and in fractional coordinates. We get the different generators. I don't have time to get into these generators, but if you're familiar with any of them, like the SU2 matrix, quaternion vectors, quaternion matrices, all this information is there. You get the translations. Let me see if I can find something that actually has a translation. This one has a translation. So this is a rotation with a translation. So we have a C2, that's a twofold rotation. And here we see the translation after the rotation in Cartesian coordinates and in fractional coordinates. You also have the choice. This is all very human readable, but you also have the choice to output this in JSON by going all the way up, and you have the output type plain text and JSON. If you click on JSON instead, you get a JSON output that you can use if you want to have it in JSON. It's a little more structured, but you can also actually use it, for example, in a JSON-L file or a JSON file, and use Python to actually work with these kind of symmetry operators. The last thing I would like to show you here is what if you want everything at once? Let me go back to plain text. What if you want everything at once? You have the crystallographic data, and extended data really gives you everything. It starts with the real space lattice, the Bravais lattice of the crystal, point group, space group. You have all the Wyckoff positions, the symmetry generators. There are a lot of them, I think 192. Yeah, there's 192. Wyckoff positions, different structure representations. We have the reciprocal cell, the atomic positions in quantum espresso format, because we have our input structure as quantum espresso, and all the cell parameters in angstrom. So if you don't know what you're looking for, use eData. It will be somewhere in there. Actually, that wasn't the last thing I wanted to show you. The very last thing I wanted to show you is we can add magnetic moments. So let's just assume we have iron and we want to give iron specific magnetic moments, and potassium and oxygen should not have any magnetic moments. So we click on the magnetic structure and we type in, let's say, 1 Bohr magneton for iron, and we use a comma separated list of spins. And we have 6 other atoms, so 6 times 0. Is that correct? Yeah, I will put that in the chat. So you can just copy and paste it. So the first iron will be spin up, the second iron will be spin down, and the rest will be 0. And let's just determine the space group. And we will see that we suddenly have a different space group. We have 216. The other space group was 227. So we have still face-centered, but it is space group 216 now instead of 227, because the spin broke the symmetry of your crystal. And later we will also have time to play with this a little bit more in the exercises. So any questions on AFLOW-SYM or on how to use the symmetry features using AFLOW Online? Don't see any questions. I don't see any raised hands. So let's move on to the second part. So we looked at structural analysis. But what we really want, or another thing that we really need, that I mentioned at the beginning of the talk, is we need to generate structures and decorate them with atoms to generate input files and discover new materials. And the question is, what could be our source for potential crystal structures for structure templates or structure prototypes? And the easy answer is, let's look at experimentally available data, and maybe there is already some compendium. The problem is that these kind of compilations of crystal structures, yeah, I said plural, there's multiple of them. That's the problem. There's not really a single source where we can turn to and say, yes, this is where we need to go. Some of them include like Pearson's Handbook, the Structure of Crystals, and the American Mineralogist Crystal Structure Database. And then there's also a German effort called Strukturbericht, which ended with the end of World War II. So there's unfortunately a lot of different works out there that crystallize, that categorize and group and define crystal prototypes and crystal structures in all their own way. There are additional hurdles to this. One is these designations can be very arbitrary. We know that, for example, sodium chloride and magnesium oxide have the same crystal structure. They're both rock salt, but sodium chloride and magnesium oxide have different mineral names, for example. Strukturbericht designation tried to make some sense of all these classifications, but the names, for example, are not very helpful. Strukturbericht designation for rock salt is B1. What does that tell you about the structure? Not much, actually nothing. You just need to know B1 is rock salt if you see it. So that's a lot of memorization that you need to do, and it is not very generalizable. On the other hand, we have the ITC, the International Tables for Crystallography, where we have space groups and Wyckoff positions and letter designations, but that requires you, the user, to have knowledge about crystallography. And there's not really like intuitive methods for materials generation. So what we try to do is we wanted to collect crystallographic prototypes and build in these prototypes into AFLOW and then try and decorate them to allow for automatic creation of new hypothetical materials. Here we have 3 examples: the Heusler structure and the anti-Heusler structure and the half-Heusler structure. And we can use this kind of framework in a high throughput manner and test a lot of different compounds using density functional theory calculations. We have 1,100 of these prototypes available in our prototype encyclopedia, which we will get to in just a minute. The prototype encyclopedia is essentially, it is what the name says, it is an encyclopedia of different crystal structure prototypes. They contain a lot of information, for example, the standard label, any kind of historic labels, the Wyckoff positions, the space group, and the lattice vectors, any kind of explicit coordinates, the Strukturbericht designation, if it's available. As I said, Strukturbericht ended with the end of World War II, so only crystals that have been long before them have an actual designation. Compounds that are similar, the Pearson symbols, basically anything that you need for this structure prototype. And so far, there have been 3 installments of that encyclopedia, amassing to currently 1,100 prototypes. And as you can see, based on how the parts developed, there's more with every volume. So who knows what part 4 is going to give us. I mentioned the standard label kind of in passing, and that is our standard label. What we didn't want to do is we didn't want to fall into the same pitfalls that, for example, Strukturbericht went into by just classifying a compound as B1. So we developed our own AFLOW prototype labeling scheme. And this is our labeling scheme. We have the reduced stoichiometry, AB, for a binary. We have the Pearson symbol, the space group number, and the Wyckoff letters. These are all used to form our prototype label. So if you know the symmetry of your prototype, your compound, which you can calculate using AFLOW, you can generate your own prototype label. But that is not enough to generate a structure because they all have degrees of freedom. Look at the this word side structure here. This is not a cubic structure. It is an hexagonal structure. So you have the lattice parameter A, and you also have lattice parameter C that's different. So to describe the word side compound, you need the lattice parameter A, and we have the lattice parameter C over A, or we have the ratio C over A, and we also have the Z1 and Z2 coordinates. Z1 is the Z coordinate of the sulfur, and Z2 is the Z coordinate of the zinc. And they're customizable using AFLOW. For example, you could change the C over A ratio to kind of squish the lattice a little bit And you can also change the Z coordinate, for example, of the sulfur, make it smaller to get it closer to the origin plane. You will see what you can do with these parameters and all that in a little bit when we go to the actual prototype encyclopedia, which we will do right now. So let's move back to our browsers. Move all the Zoom stuff out of the way. Let's go back to our browsers and back to aflow.org. aflow.org, we see the prototype encyclopedia here on the home page, and we will navigate to this one. I'll also put the link in the chat. The prototype encyclopedia is our online interface to all these prototypes, and you can use it to search for prototypes, for example, with a common name or by space group. And we will go through all of these methods. There are space group and Pearson symbols. You can look at them. You can look at Strukturbericht designations, chemical symbols. So there's a sorted list of chemical compounds. If you know a compound, you can try and look there. The prototype index is essentially a big lookup table, and crystal info I will get to in a second. It's very good and educational. All these buttons are also available down here, and we will talk about what EXTALFinder is towards the end of the talk. Crystal info is a very nice educational tool. It actually shows just information on the lattices and on the crystal systems, and essentially shows you how we define lattices orthorhombic. There's not much of a choice here, but you can see a simple orthorhombic and show which space groups belong to simple orthorhombic, and there's base-centered orthorhombic. We see the lattice vectors here and the different space group, and body-centered orthorhombic. Seems to be a problem with the math here, and face-centered orthorhombic. You see all the lattice vectors here. So you can use this essentially also as a teaching tool. If you want to know what kind of lattices and how these primitive cells look like, here's a primitive cell located inside the conventional cell. That is, when I first heard about primitive cell, took me the longest time to actually figure out is how do I visualize the primitive cell inside the conventional cell? Because I'm a chemist and I'm used to do conventional cells. So let's get back to the prototype encyclopedia homepage. Let's try and start and look for any kind of prototypes. Let's go to the space group button up top. Here we see all the prototypes are divided into different space groups. Here's the orthorhombic space group. And when you click on this one, you get all the different prototypes with an orthorhombic space group, like P222. Here's a very complex sodium niobate structure. And you can look at all the pictures to get a preview and see how the structure looks like if they look interesting. The AFLOW prototype label is always there. And we also have a chemical formula of barium sulfide that you can use to take a look. However, if you don't know the space group, or if you just know what the name of your structure is, you can use that too. We have a search bar up here, and let's look, for example, for the corundum structure. We see we have the name corundum. You can also look for anything like diamond and zinc blende, and here are some. Here's the corundum structure. You can return this one, and here we have corundum, or the megamite in there because it's similar to corundum or gamma corundum. But let's take a closer look at the corundum structure, or put that in the chat here. Just navigate to this one, and the prototype encyclopedia page on top has a structured visualization. You can just grab and take a look around here. It's a hexagonal structure. You can display, here you can actually show a supercell if you want to visualize it. I'm not going to do that here because it's already a big structure. You can display the primitive cell, which looks like this. The conventional cell, which is more of a hexagonal feature, or you can also show both. if you are not sure how how they both look like and how they relate to each other, you just show both of them here by clicking on that button. So here's how you can look at the primitive and the conventional unit cell. You can also show the Wigner side cell for anybody who knows what this is. This is a feature that's also available here. But let's go back to the conventional. Then when we scroll down, we see a lot of information on the prototype. Aluminum oxide is essentially the prototype compound. That is what the prototype is based on. The AFLOW prototype label, here we see the stoichiometry, it's aluminum 2, oxygen 3, so it's A2B3. The Pearson symbol is HR10, see that here. The space group number is 167, and C and E are the Wyckoff positions. This one has a Strukturbericht designation. Corundum was a common enough material that it has it. And here's a command for the AFLOW, software that you can use to actually generate the prototype. Then we have some information like other compounds with the structure, escolite, hematite, and ilmenite. These are all the same structure, but they have different mineral names. So you may be able to actually search for those, or if you want to know what the relationship is of corundum with other compounds, you can see that here. Here's some information or comments from us. Sometimes these have some extra comments. We will disclose any kind of uncertainty that we have with experimental data that we took it from, or here in this case, talk about the two different settings that rhombohedral and hexagonal have. And here are the primitive vectors. Here's another picture of the cell. And here are just the basis vectors, so the coordinates, the lattice coordinates of the individual atoms and the Wyckoff positions. Here we see C and E, which we had in the prototype label before. This is aluminum, these are the oxygen positions. And when we scroll further to the right, you see that this is the aluminum oxygen atom type. Here are the references where we found the structure, but the real, the real use here is this prototype generator. Here you can actually go and really create your own input files. We have VASP output, Quantum Espresso, Ames, Abinit, SIF and ELK, and also YCAR, which is a custom feature. It's not something that you use for DFT, but it's available. So let's generate it, and we can generate a VASP output. Here, this is aluminum oxide. We can also show, for those who use Quantum Espresso, you can also use Quantum Espresso. Another thing you can do here is you can adjust the degrees of freedom. So let's look at VASP a little bit more. Keep this in mind, kind of commit these a little bit to memory, and let's change the C over A ratio, for example, to 4. And regenerate it. You see that these, like the 6.34 has, or the 6.34 is new. If we change it, for example, to 3.3 went on. We have 5.236. So you can generate different structures depending on what your degrees of freedom need to be. You can also change the species. So instead of aluminum, we have iron. So you can, when you have your own prototype, you can use this to generate your own input files. And this one here is the command that you can use if you download AFLOW. You can generate this particular input file with this command in the AFLOW software. But since we don't have AFLOW installed right now, we just stick to the online feature. Any questions? Anything you want me to demonstrate here with a prototype generator? Can maybe, there's a question. Yes, please.
Yes, you are talking about generate input file, but we are not seeing where input file can be generated. It's just output that is on review.
Yes, you can just take that one and copy and paste it into, as your postcard, or for Quantum Espresso, you can just put that into your input file as is.
Okay, Marcos. Marco?
Hold on, there's a
Hello.
Can everybody use the raise hand
Hel-
feature, please? Hold on. Can you raise your hand? There's some other questions here. Christian, does that answer your question?
I have a question for you.
Yes, we have a,
Hello. Question.
yes, I understand. There's another hand before you. So there's
Okay, okay. Yeah, I'm here, please.
Mm-hmm.
Yeah, what I want to ask is, okay, now for instance, the rock structure, the salt rock structure, that is NaCl.
Yes,
Now,
rock salt structure, yeah.
Exactly. So if I want to build a particular material with that structure,
Yes.
so is it that I'm going to search for it in the prototype, then try to adjust the lattice parameter?
Mm-hmm. We can actually do that right now. I can demonstrate that real quick.
Thanks.
So what I would do is, I mean, if you don't know what the space group is, but you can also just take in rock salt here in the search page. It should come up as rock salt here. You click on that one, and then you go all the way to the bottom. And I mean, we want, let's say we want magnesium and oxide, and we lattice parameter, I don't know, 6.6.2. And here's your input file. Yes, you can just look for rock salt or look through the prototypes or search for your particular rock prototype and do it the same way. Yeah.
Okay, one more thing, please.
Mm-hmm.
Okay,
Yep.
now this is actually a binary system.
Yes.
So what if I want to work with maybe ternary or quaternary?
Then you need to find the right prototype. So
In the sense that I want to use this rock salt to build a ternary system.
in that case, I'll go to the space group.
Okay.
We know rock salt is 202 is cubic, at least maybe 225 face center cubic. And what I would do if you wanted to look at the rock salt space group, you go all the way to 225, and then I would find the prototype that is closest to what you need. So it's a ternary. Yeah, it's hard to tell because a ternary rock salt doesn't really exist. You will need to find what the actual correct structure is, or if you have a postcard or if you have an input file already with something similar, AFLOW can help you determine what the correct prototype label is. And we will get to that in a little bit, actually, if you already have a structure file. But other than that, I would look for the correct prototype and use whatever you think is good.
Okay, sorry. Actually, the file, I don't have it yet. I don't have it. It doesn't exist. I just want to build it because I build it with rock salt structure, because mostly from some of the papers being read is that, okay, they use rock salt to build that particular system.
Right, but
So
an actual rock salt structure is binary. So what you're looking for is a rock salt like structure, and in that case, you will need to find something that is already similar. We were talking about prototype generation using AFLOW. The AFLOW software itself, is probably a little bit more what you're looking for, because you don't rely on us actually having the prototype in the encyclopedia. If we do have in our AFLOW school page, I can send that link out as put that in the chat. There are some more tutorials that are actually looking at the command line utility, and that may be what you're looking for.
All right, it's okay. I'll check that.
Thank you for the question. Muyiwa, you had a question.
Oh, you have answered the question. Hello?
Yes, I can hear you.
Hello?
Hello? What is your question?
Yeah, you have answered the question. My question is that you have given us example with two atoms. I just want to know how to deal with more than two atoms, which of course you have answered it.
Excellent. Great, I can answer your question. Yes, you just need to find the right prototype, and with the AFLOW command line, you have more flexibility. What you need to know is the Wyckoff position, the space group, and the Pearson symbol, which you can determine with AFLOW.
Okay.
Any other questions? I don't see any. So let's go back to the slides. So the slides also contain an overview of the prototype encyclopedia and what we can and how everything looks like and what you find there. But I want to do one last thing, and that is our AFLOW-XtalFinder functionality. So we learned how to describe the symmetry of a material, and we also learned how to generate structures based on a prototype or the structure template and decorating them with atoms. So the last thing we are looking for is how can we actually determine how similar structures are? And that's what AFLOW-XtalFinder does. Why do we actually care about doing this? There's two use cases, actually three. One is to mitigate duplicates. You can imagine that when you do data mining on, let's say, a set of experimental structures, you want to gather statistics about how common certain prototypes are and structure blueprints are. You need a good tool that can compare structures and actually determine how similar they are. Another good thing is for machine learning. Oh, I actually saw a question pop up. How can crystal symmetry related to Python coding to predict its electronic properties? I will get to that kind of towards the very end. We do have a Python wrapper, but it does require installing AFLOW. All of the things we have, or all the symmetry stuff, is printable as JSON. So if you use the AFLOW command line tool, or if you use the online feature and copy and paste everything into a JSON file, you can use Python to actually look at all the symmetry information. Predicting electronic properties, you will have to run DFT code yourself if you have a structure that you're interested in. Unfortunately, we cannot run DFT for everybody in our servers. I wish we had those resources. But yeah, going back to the XtalFinder functionality. So one thing that we need, that we have good use case for to look at comparison of structures and figuring out similarity is gathering statistics, but also for machine learning. A similarity can be an important part of your feature vector, but the other one is to filter out duplicates. If you have a set of structures and you're training your machine learning model on that set of structures, and it turns out you have a lot of duplicates or similar structures, you're going to bias your model. The other one is we can use XtalFinder to identify prototypes, determine the symmetry, and maybe check if a prototype already exists in the database. This is very, very difficult to do by hand. When we look at the right-hand side, these three structures, just looking at them and determining are they the same, are they different, just by the naked eye is difficult, and it takes typically a lot of effort to really figure this out. These three look different. They look different, especially number 3, the one at the bottom, but they're actually the same structure. And doing this by naked eye and doing this manually is just not a feasible task, especially not for a lot of different structures or for a large set. That's why Dr. David Hicks developed XtalFinder. It is using the same principles to determine similarities and to determine prototypes as AFLOW-SYM. It does a tolerance scan, determines the symmetries, and uses the tight tolerance to determine the symmetry elements and figure out what the prototype designations are. And as you can see here with this kind of tolerance scan, it can lead to very, very different results. And we found that this 1% of the minimum distance is the most consistent with experiment. So AFLOW-XtalFinder can determine a AFLOW prototype based on the input structure that we give it. And I will show that in just a minute on AFLOW Online. What it can do as well is not just determine the prototype label, but also what the degrees of freedom are here for this particular structure. Looks like corundum. It can determine what degrees of freedom we need, and for aluminum oxide, it also determines some default parameters. But ideally, or it determines the parameters based on the input structure that you give it, and you can regenerate it using AFLOW to convert it back into a postcard. How does EXTLFinder determine similarity? There's essentially a 3-layer process to this. There's 3 different ways we determine similarity. One is we're looking for whether or not the structures are isopointal, which means that they have the same symmetry. If 2 structures have completely different symmetry, they are they are not the same structure. Same structures have to have the same symmetry. Another layer of this is looking at local snapshots. If the local environment around the atom is different in different structures, we do not have the same structure. The most robust method, though, is the isoconfigurational method, where EXTLFinder is trying to find the common lattice and the common origin and tries to match the structures. And then what it does is it determines the distance between the original structure and the mapped structure. And depending on how far the atoms are apart, it determines a misfit parameter, and the larger the misfit is, the dissimilar are the compounds. Another thing that EXTLFinder can do is can compare to the AFLOW database in 2 ways. It can check whether or not the prototype of your compound already exists with AFLOW, and it can also check whether or not the actual compound that you have exists in the AFLOW database. So if you're curious to see, do I have to actually calculate this material, or does AFLOW already have it for me? You can look at it, and you can use EXTLFinder to see, do we have the compound, and if not, does AFLOW have the property that I'm interested in using AFLOWs? And that is what we did. For example, sodium chloride, we did a database search and found that we have a few very similar compounds with very small misfit. And something that we found is that we have very similar enthalpy per atom with a similar misfit. So that's good that similar compounds also produce similar enthalpies per atom based on DFT. And if you use the AFLOW software, the command line function, you have a lot more options. I encourage you all to look at the EXTLFinder videos for the command line on our AFLOW school page if you want to learn a lot more about AFLOW, the EXTLFinder. There's a lot of functionality out there that I cannot get into because of time, and we don't have the AFLOW installed right now. We have an AFLOW online interface, and this is exactly where I'm going to go to. So I'm going to share the browser again. And we're going to leave the prototype encyclopedia and go back to AFLOW online. Well, first of all, are there any questions about EXTLFinder? But what the point of it is? We will see it in action in just a bit. Doesn't appear to be the case. So we're going down below symmetry. We still have our iron potassium oxide structure. We're going down below symmetry, and here you see structure comparison, or EXTLFinder. There are 3 different apps that I would like you to be aware of. Oh yeah, first of all, the stuff above symmetry, the stuff that I said I will talk about later, the AFLOW prototype label. This is a feature you can use to actually determine which prototype you need to use. So let's do that first. And you see, this is the AFLOW prototype label based on the input file that I put in. And you can also use Quantum Espresso. You can use any kind of input format, just like we did before. And this is the prototype label. So if you want to know whether or not what the AFLOW prototype of your input structure is, you can use the AFLOW prototype feature, and it returns not only what the label is, but also what parameters you need, what degrees of freedom you have. This one is a highly symmetric cubic structure, so it only has the lattice parameter, but for corundum, we saw we have a lot more. We have Z coordinates and we have a C over A ratio. So that's the AFLOW prototype. Another thing we can do, what I said earlier, we can compare to different databases. We can compare to the AFLOW database. We can compare to prototypes. We can also get the isopointal prototypes in case we have two similar prototypes that have the same symmetry. Can get that as well. But let's compare to the AFLOW database. Do we have a structure like this in the AFLOW database already? Yeah, and it turns out we do. So this one here says we have a duplicate structure, a duplicate compound, and this is the AURL. Dr. Rose talked about it yesterday. This is the AURL of the structure that we have in the database. So if you're unsure whether or not we have this in the database, just run compared to AFLOW database and you will get the answer. We can put that in the browser and actually take a quick look at the REST API. This contains all the data with all the properties that we're interested in. So check out before you do your own calculations, maybe if we have it already done, or if you want to benchmark your calculations against ours, here are all the properties that you can look at and compare with your own calculations. Close a few of the tabs. Okay. The other thing that you can compare to is to our prototype encyclopedia. If you are not sure whether or not we already have your structure prototype, then you can, instead of compare to the AFLOW database, we can compare to prototypes. And it turns out we already do. If you compare this to the prototype label, we have AB2C. Just commit the AB2C to memory here and compare it with here. You see there's ABC2, and that's because AFLOW by default sorts all the species alphabetically, but the prototypes might be modeled after experimental formulas. So could be a little different, but they're all equivalent. These are the same prototypes. You see the misfit here is 0. It's the same thing. So that's one way you compare. You can compare this with the prototype database and see if we already have it. If we don't have it, you can still generate your input files with AFLOW. So not having it in the database is not a problem for you. The last thing is the unique atom decorations. It essentially tells you in which sequence you can decorate your atoms. This is the mostly a permutation of the atoms that you have, but this is also an option that is available. So this is a comparison to the database. What if you are not sure whether or not you will have two structures and they're the same? Can you use AFLOW Online for that? And that question was obviously rhetorical. Yes, you can. We have this compare structure feature. Here you see two different structures. They're both aluminum oxide, but they have, as you can see, different lattices and slightly different atomic positions. Are they the same? And for that, you can use the compare structures feature. And here's comparison mode. And there's materials and structures. And I'm going to show you what the difference is by adding a third structure. I'm just copying over the aluminum oxide structure, add a new structure with a plus button, and just paste it, and just change aluminum to iron. That's all I'm doing. So there's three structures, one that are completely identical, but with different elements. And here's a structure that we don't know anything about. So when we do comparison mode with materials, we see that it says list of duplicates, file structure 2 out of 3. So it means that the second structure and the first structure are identical, but the iron oxide structure says it has no duplicates. When we do the comparison mode of structures, we suddenly see everything as duplicate. So what is the difference here? Compare structures with materials, take the species into account. So for aluminum oxide and iron oxide, it essentially looked at iron oxide and aluminum oxide, says these are not the same species, they cannot be the same material. The structures, however, does not look at what the species are. It essentially just looks A and B. It looks at A and B. Aluminum and iron are just considered to be the same species, and oxygen is considered to be a different species. That is the difference. It doesn't care whether or not you have different atoms. That's the big difference. Our online feature here can compare up to 8 structures. So if you want to compare a large set of data, you need to download the AFLOW software and work with this one. Any questions about the AFLOW-XtalFinder feature? If that is not the case, I have some exercises for you. Here are, you should also find them in the slides, and you can play a little bit with those. And why don't you work on this for the next maybe 15 minutes, and then I will go over them myself. Thank you. Okay, let's go to exercise number 1. For that, I move back to the browser. And find the link. So your task was to follow that particular prototype and generate a geometry file. It's cadmium rhenium oxide. And for that, you go just all the way down and just generate the input structure. Fast quantum espresso wrap in it, doesn't really matter. So you just copy everything, highlight everything, and copy, and then you go to AFLOW Online. Let's actually just reload it to get rid of all the output. You paste the structure in here, and then the question was to use different symmetry tolerances for tight and loose. Here's the symmetry tolerance up here, and let's determine the space group. Space group here is 119. What if we do looser symmetry tolerance? See, it actually took a little longer, but now it thinks it's actually cubic. So here you see how the symmetry tolerance can have an effect. Thinks it has space group 227, and here thinks it has space group 119. So tolerance is important. Tight or loose can make a difference. The next one was to just play with magnetism a little bit. This was this structure here. This is an iron carbide. So let's do the same thing we did before. We just generate a input structure. There's 1 carbon, 4 irons. Just copy and paste the structure. Let's just generate the space group or Wyckoff positions. Non-spin polarization, we have 1 carbon and we have 1 iron, so they're all equivalent. Space group is 215. So now let's add some spins. I said in the exercise that carbon needs to be 0, but other than that, you can be as creative as you like. I'm just gonna do 1, -1, 1, -1. So basically a certain antiferromagnetic configuration, and we do the same calculation. We just do the same Wyckoff positions. And what we see is that we suddenly have 2 iron atoms here in space group number 35. So this is by taking spin into account. If you were, for example, to use -3, some kind of hypothetical ferri magnet, we will see 3 inequivalent irons and space group number 8. So it goes, keeps going down. Symmetry keeps getting lower the more atoms we add. Number 3 was to go to specific AFLOW entry. The entry page will load. And then go to the downloadable files section. You can just click on here and you get there. And get the BAS concar. You can also get the QE geometry. It doesn't matter. AFLOW Online doesn't care about the structure format. Take that one. And then you determine the prototype designation. Just by pasting it in here, get rid of the magnetic structure. Otherwise you might get an error. And we get the AFLOW prototype label. And what we see here is we get the prototype label and we get certain degrees of freedom. We have the B over A ratio, the C over A ratio, Z1, Z2, Z3, and it even determines the parameter values for that particular entry, for that particular structure. You can get all that here. If we go to this one, if we actually go to the structure, you should see the same information here. Here you see the parameter values in this table and the prototype label in the entry page. So we have all that information, but you can also determine it using AFLOW Online. The last task was to go to the prototype encyclopedia and look for rock salt. I've already been there earlier, but in order to get there, you can just type rock salt and go to the rock salt prototype. And just using the default parameters, we generate the input structure. And back to AFLOW Online, we paste it in the input structure and clicking on compare to library, compare to AFLOW database, hit submit, see how many duplicates we get. It will take a little bit longer because it has to go through all 3.5 million entries, but I will get there eventually. Any questions while this is loading about the exercises? Here we see we have a bunch of ICSD data and some prototypes when we did some hypothetical calculations. So it looks like a lot of them relax to similar compounds, structures. Are there any questions? That does not appear to be the case, so I will just finish up. Somebody asked earlier about Python. Do we have a Python interface, or how can we use Python with that? There is an option. First, you need to install AFLOW. And we have Python modules that you can generate by running AFLOW, but there's also in the install AFLOW section, there's installation options, how you can install your own virtual environment with the AFLOW modules. But these are the ways to get to Python. The AFLOW schools videos have a lot of tutorials on how to do this, where we had a lot more time to actually go through that. Look for Dr. David Hicks videos about AFLOW-SYM, XtalFinder, and Prototype Encyclopedia, and you will find tutorials on how to interface your Python scripts with AFLOW. And yes, for more information, feel free to look at the READMEs in AFLOW, and there's a bunch of papers. They're all given here The part 3 by now is actually out. AFLOW-XtalFinder is the source of for XtalFinder and AFLOW-SYM. You can see maybe a little bit more technical details about how AFLOW-SYM works. That concludes my talk. Thank you very much for your attention and for all your good questions, your participation. If you have any more questions, please put them in the chat or raise your hand. And does AFLOW have a manual? Not a comprehensive one yet. We do have readmes for all the modules, so you would have to look at it. The best way actually to learn AFLOW instead of reading through a manual, in my opinion, is watching the videos. We have a very structured tutorials from the past. There's a question. Ibrahim, please unmute yourself and ask your question.
All right. It's about this comparison function. As you mentioned earlier, in the symmetry, there is 1 and 10% tolerance in case of symmetry. Does this apply to comparison, or there is another criteria in terms of comparing accuracy?
I think comparison can take a tolerance too. Yes. The default is the tight tolerance.
Okay.
Good question, though. Very, very good question. Any other questions? I do not see any questions or any raised hands. Thank you again for being here, for participating. And we will see you all tomorrow, where Dr. Coriosis is going to talk about the thermodynamic stability, synthesizability, and how to correct formation enthalpies for polar materials.